Inside any interior space, light is the primary force dictating function, mood, and visual quality. But mastering how that space feels requires moving past qualitative descriptions and into rigorous quantitative science. There is a common misconception that simply purchasing a brighter light bulb will guarantee a well-lit environment. To understand the true behavior of light, we must break the physical phenomenon down into exact sequential units of measurement. Without this mathematical precision, designers are forced to rely on guesswork, a process that frequently results in high-end spaces that feel visually uncomfortable or functionally impaired. The physical sequence of light starts with the lumen. This is the starting point at the hardware itself. The second unit is the candela, which dictates the directionality of the source. The final destination is measured in lux. This is where light physically interacts with the environment. These three units track a strict physical timeline. Light is emitted, it travels through space, and it lands on a target. The central error in many architectural lighting designs is conflating a unit of emission, the lumen, with the unit of received light, the lux. To understand emission, ignore the room. Ignore the walls, the floors, and the distance. Focus entirely on the origin point of the light. This origin point produces luminous flux, measured in lumens. This is the absolute total amount of visible light pushed out by the source in all directions simultaneously. Lumens are the standard metric printed on consumer packaging because they represent the raw maximum power capability of the hardware. However, measuring total power tells the designer nothing about where that light is actually aimed. To track direction, we use luminous intensity, measured in candelas. This calculates the precise amount of light pushed in one specific focused angle. As a historical baseline, one candela is roughly equivalent to the directional intensity produced by a single standardized wax candle. Lumen and candela only measure what the hardware produces. They cannot predict how bright a desk or a hallway will actually feel to the occupant. We must now shift our focus away from the hardware and onto the physical surfaces of the room, attempting to capture that light. This diagram outlines that capture. Illuminance, measured in lux, is the quantity of visible light landing on a defined plane. It is the metric designers use to determine how bright a surface appears. Mathematically, 1 lux equals 1 lumen distributed evenly over a 1 square meter area. Consider a scenario where a luminaire projects exactly 1,000 lumens onto a perfectly sized 1 square meter floor plate. That specific floor plate receives exactly 1,000 lux of illuminance. But if that same 1,000 lumen output is forced to spread across a 10 square meter floor plate, the resulting illuminance drops to only 100 lux. Lux is inextricably tethered to surface area. A high lumen bulb will still create a dark, poorly lit environment if its output is spread too thin. That spread is dictated by physical distance from the source, the variable that often complicates amateur lighting calculations. This model tracks traveling light. As it moves, it radiates outward into a wider cone. The total lumens never decrease, but the surface area expands. At 1 meter, the light strikes a concentrated area, yielding 100 lux. At 2 meters, a geometric shift occurs. The linear distance doubled, but the surface area is now 4 times larger. Illuminance plummets to 25 lux. By 3 meters, the area expands to 9 times its original size, and illuminance drops to a mere 11.1 lux. This geometry explains why a ceiling fixture can be painfully bright to look at, yet provide virtually no usable light to a desk just a few meters below. This severe geometric decay is the primary challenge that separates amateur bulb buying from professional photometric engineering. Specifying a lighting layout based solely on lumens is ineffective because distance dictates the only metric that matters to the occupant, the final lux. We must move out of abstract geometry and into the practical reality of targeting specific lux levels for human activity. Human eyes are adapted to extreme ranges of light, requiring designers to calibrate artificial environments to highly specific tasks. This chart sets our maximum benchmark. Ambient daylight operates on a massive scale, ranging from 10,000 to 25,000 lux. In contrast, an overcast day still delivers a potent 1,000 lux of illumination. Even a sunset provides roughly 400 lux. Against these natural numbers, architectural reality is stark. Almost all artificial commercial lighting is engineered to operate strictly at or below the 1000 lux threshold. Because interior environments operate in such a narrow margin of light, there is zero room for error when calculating geometric light decay. The professional lighting designer's job is an exercise in reverse engineering human comfort. The process always starts backward, first determining the exact lux required at the destination surface based on the human activity happening there. Only after the target lux and the geometric distance are known can the designer move backward to specify the necessary Lumen and Candela hardware. Ignoring this sequence leads to spaces that are functionally impaired and visually uncomfortable. Successful lighting design is achieved by mathematically controlling the geometry of light to deliver precise illumination exactly where the eye needs it, rather than relying on the raw power of the source.